In this lecture, we're going to discuss the Borsuk-Ulam theorem, and we will also prove it. And then the follow-up lecture, which will be our last lecture, we would see how you can use this theorem to solve a famous problem that was unsolved in combinatorics. So that's a very surprising connection between topology and combinatorics, and this theorem is like that key result that makes this work out. So let's begin with the statement of the theorem. Here's a theorem. So the theorem here is if F is a map from the two-dimensional sphere to R2, of course this is a continuous map, then we can find a point P on S2 so that F of P and F of minus P get mapped to the same location in R2. So what this is basically saying, to draw a picture, is that if you have your sphere and you have your plane and you have some kind of mapping, you have some way to map that sphere to the plane, then you can find the point so that the point and the negative of the point. Now, we should understand, I think this would be convenient, we can think of the sphere. This is not required, but I think this is helpful. You can think of the two-dimensional sphere as the collection of points, let's call them x0, x1, x2. So these are points in R3 with the condition that their sum of squares adds up to 1. So then if this, you call that P, the negative P is just a negative when you make all of these coordinates negative. So on the picture, what we're saying is you can find the point P somewhere, and the point that's opposite of it, that would be negative P. So these are called antipodal points. So antipodal points means that they are on the opposite side of the center. So you would have a line connecting them through the center. So you would have 2 points on the opposite side on this diameter that's passing through the center. So you have 2 opposite points. So the technical term is antipodal points. They get mapped to the same position in R2. So that is the Borsuk-Ulam theorem. So that's a pretty surprising theorem. And here's an interesting interpretation, a surprising interpretation of this theorem. So it would say this. So on Earth is a two-dimensional sphere, we can find 2 points directly opposite each other. So the opposite, you would say the opposite, like extremely opposite across the world, right? Directly opposite across the world, which have the same temperature and humidity. Which is kind of surprising, because like if I told you that on Earth right now you can find 2 points on Earth that are directly opposite each other and they have the exact same temperature, that's pretty interesting. But we're saying even more than that. Not only can you find 2 points that are directly opposite each other with the same temperature, but their humidity levels will also be the same. And I mean, this is really what we're doing, because temperature is a real number, humidity is a real number. So together they give you a point in R2, right? That's a pair of numbers. And you have a mapping that assigns for every point on Earth a temperature and humidity value. And that's a continuous mapping, of course, because the temperature does not abruptly go from freezing to hot instantly. It gradually changes. So temperature and humidity are continuous functions. And therefore, as a consequence of the Borsuk-Ulam theorem, we have this very surprising result. Now, also, many of you might be interested, is there something special about the two-dimensional sphere? And of course not. The theorem can be generalized. So you can, of course, replace the two-dimensional sphere by the n-dimensional sphere, and you replace this by the n-dimensional Euclidean space, and the result will be the same, that you can find a point P. So a point will just be something that has n plus 1 coordinates that add up to 1. Sum of squares is 1. So points that are directly opposite each other with that property. So it does generalize, but unfortunately, we would not have the tools to prove something like this. This is a theme that we had throughout this course, that we often prove results maybe in dimensions 2 or 3, but we do not prove it beyond that because the fundamental group or the other tools that we have, they sort of lack power in higher dimensions. So we're going to have to leave the generalized Borsuk-Ulam theorem for a continuation course in topology. Actually, the proof of the generalized theorem for any degree would be exactly the same, except there's going to be a certain obstacle, as you're about to see, that's going to prevent us from doing that. And once we have the tool of homology, then we'll be able to make the proof work for an arbitrary number of dimensions. But for a first course in topology, let's just prove it the standard way for the two-dimensional sphere. And it's going to be based, so the proof of the Borsuk-Ulam theorem is based on something called degree theory. Of spheres. And I think this was introduced, I might have people messed up, but I think this was introduced by a mathematician called Heinz Hoff. So he introduced this notion of degree. So basically, what this is that whenever we have a continuous map, F, let's say from the n-dimensional sphere to the n-dimensional sphere, there is a notion that's called the degree of F that has certain properties. The degree is an integer and all that stuff. So this is what we call degree theory. This happens to be very useful when one is working on manifolds. So when you're working on a manifold, you can pick a point, and then on that point, you have a neighborhood. That neighborhood is homeomorphic to Rn. And let's say this manifold is then being mapped to another manifold, and you have another point, and you have another neighborhood that's homeomorphic to Rn. And now, if you have some point that's being mapped to another point, if you were to delete this point, if you remove this point, then the remaining region that you have, it homotopes to an n-dimensional sphere. And so you have a mapping from the n-dimensional sphere to the n-dimensional sphere. And so degree theory, it permits you to, it almost feels a little bit like differentiation. In calculus, we talk about often, for instance, like the Taylor series. We take a function, we expand it into an infinite series, and then we look like at the order of vanishing, how high do we go in the degree until things begin to vanish. So it feels a little bit reminiscent of that, but this is a different approach because here we're not using calculus, we're not using infinite series, we're not using differentiation or anything like this. We're doing this in a purely topological way. And this is what is referred to as degree theory, and it's sometimes useful. It's sort of plays the role of a derivative in topology in some sense. And in order to define degree theory, you have to use homology groups, which we do not know yet, so we have to avoid. So we're going to develop, so what we'll do instead is we're going to develop something called degree theory of circles, just of circles. So we're going to have a continuous map from S1 to S1. And we would like to find something called the degree of your mapping. Now, before we define that, I want to give you some examples first so that we have an idea of what the degree should be equal to before we even define it. And then we'll see how to define it. In fact, maybe you'll even be able to come up with your own definition, with your own way of doing this. But basically, we have this. So let's look at some examples. So we commonly think of the one-dimensional sphere or the circle. We think of these as complex numbers whose norm is equal to 1. And now imagine you have a function from S1 to S1. And let's say we have the identity. So this is the identity. So for the identity, I think we would agree that the degree should be 1 because it's the identity. But also, if you look at the formula for f of z, notice z appears to power 1. So it makes sense that it should have degree 1. Now let's say you have f of z is equal to, let's say this is negative z. What should the degree be? Well, the degree should still be 1. Even though it's negative, if you look at the power on z, the power is still 1. Or maybe you can even visualize what this function is doing. So here's basically what the function is doing. If you have a point z, negative z is on the other side. So essentially what this function is doing, it's taking your circle and it performs a 180-degree rotation. So if you have a closed loop, that closed loop has the same orientation and it goes around once and it spins around once. The only thing you're changing is you're changing where the loop starts and ends. But other than that, everything sort of stays the same. So it makes sense that degree should be 1. Or let's say we have another example. Let's say we have z squared. Z squared. So with z squared, because we have a power of 2, it's reasonable to say the degree should be equal to 2. Okay, so we have that. And also, pictorially, this should make sense. Because we actually talked about this when we proved the fundamental theorem of algebra, that if we kind of travel around one time counterclockwise, if you do z squared, you're sort of going twice as fast. And so the picture would be that your image loop would go around twice. It would go around twice, and so the degree should be 2. So it winds around 2 times. So that makes sense. Another example would be, let's say we use the conjugate map. So the conjugate map, z goes to its conjugate. That's the complex conjugate. So if we just look at the picture of what's happening here, this is our circle. Imagine you have a loop that goes like this. It goes counterclockwise. Well, the conjugate means you flip it. You're going to have to flip it. So the geometric way you get the conjugate is you flip everything across. So it's like a reflection. And when you take a reflection, you're going to change the orientation. And so instead of going counterclockwise, it would now go clockwise like this. So it makes sense that in this case, the degree of f should be negative 1. But there's another way why the degree should be negative 1. And it has to do with this, that we know that if you take a complex number and you multiply by its complex conjugate, you get the sum of squares of the 2 components. So you get the absolute value of z squared, but that's equal to 1. And so the complex conjugate, so the reason why this is equal to 1 is precisely because we're on the unit circle. And so the conjugate is equal to 1 over z. And if you write it as a power, that's z to the negative 1. So notice you have the degree on the z variable appears to the negative 1 power. So it makes sense why the degree is negative 1. Now, the thing is that functions from the unit circle to the unit circle can be rather complicated. All of the examples that we currently gave with various powers of z, those are easy to understand, but you can imagine some very highly convoluted function that has nothing to do with polynomials, and we still want to talk about the degree. We want to talk about the degree in general. So here's how we define it. So the standard loop in S1 is the path that's given by e to the 2 pi I t as t ranges from 0 to 1. So that will trace out a path for you counterclockwise exactly one time around. And that's exactly the same path we used many times before. We used it in the fundamental theorem of algebra. We used it when we talked about the homotopy group of S1 and all that stuff. So here's how we define it. We define the degree of f. So this is by definition, this is how we define the degree. We apply f to this loop. This is exactly what we did in those pictures. So this is a closed loop, and this is the image loop. So basically, e to the 2 pi I t, it's just a standard loop that goes around over here, like this counterclockwise. And f of e to the 2 pi I t, well, that's the image loop. It can be quite complicated. Maybe it goes forward, maybe it goes backtracks. Well, I mean, it's kind of hard to draw it because everything's one-dimensional, but we talked about this before. Maybe it kind of goes like this, then it goes back, then it goes forward again, it goes back, it does a full revolution, it comes back. Well, I'm not going to try to draw it. But this is just the image loop under this f. So this is a closed loop, and you're just going to calculate the winding number of that closed loop. So this is going to be some kind of closed loop. It will wind around the origin in the complex plane, and you will calculate its winding number. And whatever winding number that is an integer. And so the degree of every continuous function is going to be an integer. And you can check that all of the previous examples that we did, they're consistent with this definition. You can also check that if f is the constant map, so this is the map that sends everything to a single point, then without any surprise, the degree should be 0. Because then the image loop is just a constant loop, and the winding number of the constant loop is 0. Now the issue is, the reason why we cannot generalize this kind of approach to higher dimensions has to do with the simple fact that there is no notion of a winding number in n dimensions. So we do not have that. So because of that, we have to do something else if we want to generalize this concept of a degree of a mapping. But for the purposes that we're doing right now, this is actually good enough for us. We'll be able to prove the Borsuk-Ulam theorem using this idea for dimension 2 case. So at least that's something. And I want to mention, so we need 2 technical lemmas to prove the Borsuk-Ulam theorem. So these are the lemmas that we typically do not care about in general. What we really care about is the Borsuk-Ulam theorem. And it's just like one of those things that you need some lemmas, you have to get some lemmas out of the way in order to make the proof work. So let me start with this first lemma. See, this is lemma 1. So suppose f is a map from S1 to S1, and it has the property that f of negative z is equal to f of negative f of z. Then the degree of f is an odd integer. Now, before we say anything, let's just think about this intuitively. See if this makes sense. Notice that we're saying that, well, maybe I should add this condition. This is, of course, for all z on the unit circle. So if you take a complex number, if you take a negative of a complex number, then f of that would be negative of f of z, of the original z. So it says that you can take out the negative sign and put it in front of f. So this is, you probably heard, know what we mean by this. This is often what we call an odd function in, like, I'm not even sure, is it like pre-calculus? Is that what they call it, an odd function? That if you can replace a negative variable by a negative sign, then that means you have like odd powers. So the fact that we have such a lemma is not really surprising. This is almost saying that f is like, in the simple case, if f maps z to a power of z, then the exponent has to be an odd integer. But of course, this is a general mapping. You do not really know anything about how it looks like. So that's the first lemma. So this is a believable. I mean, it's quite believable, but it requires proof because you really do not know anything about how f looks like. And you have to resort back to the definition of the winding number for this to work. But let's do this. Let's accept this lemma for now. This lemma is a little bit technical. I do not want to prove it at the moment. I'm going to return back to it. I want to mention lemma 2, and then we'll prove the Borsuk-Ulam theorem, and then we'll return back to lemma 1. So this is lemma 2. So lemma 2 says is that there is no map from the two-dimensional sphere to the one-dimensional sphere with the property that f of minus p is equal to minus f of p for all p on S2 on the two-dimensional sphere. So notice in this version, in lemma 1, we're mapping the one-dimensional sphere to the one-dimensional sphere, and in lemma 2, we're mapping the two-dimensional sphere to the one-dimensional sphere. Now, so what I'm going to do is I'm going to prove to you lemma 2 using a picture. And it's going to be, think of it as a homework problem for you to write it out a little bit more carefully. But I think the picture would be fairly convincing, and you'll see how it works. So let's draw a picture for what's happening here. I also want to make just a small little observation. Notice over here I'm calling it z, and over here I'm calling it p. The reason is just very simple, because we often think of the one-dimensional sphere using complex numbers, whereas a two-dimensional sphere, we're not thinking of it using complex numbers. We would just think of p, so this point p, it's a coordinate of 3 real numbers whose squares add up to 1. So it's just a notational thing, but that's just to explain why I'm suddenly using a different letter to do it. So let me show you a pictorial proof. So this is a pictorial proof, and it's an exercise to write this into a more careful proof. But as you will see, the picture is pretty convincing. So let's say what the f is doing. The f, our function, it's taking the two-dimensional sphere and it's mapping it to the one-dimensional circle. Now, look at the equator. So look at this equator. Maybe I should use a different color. So if you restrict everything down to the equator, so let's say this. If we restrict everything down to the equator, then we have a mapping from the equator to the circle. Now, I could call this mapping f again, but technically we're restricting f to a subset. So maybe we'll just call it g. Okay, so this is just a restriction. So G is F restricted to its equator. So it's basically the exact same mapping. Now, what property are we assuming? Okay, so we want to show there is no such map. So this is like a proof by contradiction. You assume you have such a map, and you get a contradiction out of it. So let's say we have a map. Now this map has the property that if you take the negative of the point, it's the negative of the point. So let's say we pick a point on the equator, right? So if this is P, the point over there is negative P. Okay, so we're saying that if you take two antipodal points on the equator, right, on the circle, antipodal points on the circle, G maps the antipodal points to negatives of each other. So this would mean, so by lemma 1, the degree of G is odd. Okay. However, S2 is simply connected. So its equator can be shrunk to a point. Therefore, the degree of G would be the same thing as the degree of a constant mapping. The reason for this is because the winding number, let me go back a little bit. Recall how the degree is defined. The way we define the degree is we take the standard counterclockwise loop, we apply the mapping to it, we look at the image loop, and we find the winding number. So the degree is defined in terms of the winding number. The winding number is a homotopy invariant. G, the mapping on this equator, you can shrink the equator down to a point. So G, this mapping, is homotopic to a constant mapping. And so the winding number of G is the same thing as the winding number of a constant path, which is 0. So then the degree of G is equal to 0. And that's the contradiction. The degree of G is odd, and the degree is equal to 0. So that's our contradiction. So I think this is a nice argument. You can, of course, find books that write it out more carefully, but I'm always a bigger fan of trying to find a nice intuitive argument and then figure out a way how to take that picture and formalize it into something that's like more mathematically appropriate. But as far as thinking about math is concerned, the way we come up with proofs in math is we always have these intuitive pictures in mind, and we use them as motivation to write out a proof. So that's why it's important to think pictorially as much as you can and develop the skill of converting pictures to rigorous proofs. So let's accept this as the proof of lemma 2. You can see that lemma 2 depends on lemma 1. So we do have to prove lemma 1. But for the moment, let's not prove lemma 1 and now show how we can prove the Borsuk-Ulam theorem. Okay, so let's state the theorem again so we know what we're trying to prove. We're going to say that f is a function from S2 to R2. So we have a map from S2 to R2. Of course, a continuous map, we're not even going to bother to say that. There is a point on S2 so that f of p and f of negative p are equal to each other. And now let's give a proof of this. the proof is actually quite simple once you have the lemmas. And this proof that we're about to say, it generalizes to n-dimensional space also. The only problem is the two lemmas need to be proven. And the two lemmas are actually proven the same way, but you have to develop degree theory on arbitrary spheres. So everything we're doing does nicely generalize, except we do not have homology groups in order to generalize degree. So here's how the proof goes. You assume, so suppose, for the sake of contradiction, that f of x is not equal to f of negative x for any x on S2. So you're trying to show there exists such a point. So you assume opposite, that for any point on S2, f of x and f of negative x will always be different. And now you're going to construct. Actually, this proof does feel a little bit similar to Brouwer's fixed point theorem. You assume that two things are not equal, and then you can construct something out of it. But of course, this is a totally different theorem, and you're using different tools to prove it, but it does, in some sense, feel kind of similar. You're going to construct the map. Let's call this map G. And this map will go from S2 to S1. And is going to be constructed by the rule that G of x. So here's what we'll do. We'll do f of x. Then we will subtract f of negative x. And then we will divide that by the Euclidean, the two-dimensional Euclidean norm of f of x minus f of minus x. Okay, so let's just understand that this makes sense. The function takes a point on the sphere. F of x assigns for you a point in the plane. So this is a point in the plane, that's a point in the plane. We're assuming they're not equal to each other. So when you subtract them, so if you think of these as vectors and you subtract them, that's going to give you a non-zero vector in R2. And you're just renormalizing that vector. You're turning into a unit vector. So a unit vector can be positioned on the sphere, right? This is, you have two components, right? This is into R2. So you have a pair of numbers that are normalized to have unit length. So that is exactly the one-dimensional sphere. So whatever this is on the one-dimensional sphere. Now you should notice that the assumption that f of x and f of negative x not being equal to each other ensures that the denominator is not zero, so we can divide out by this. And that also tells us that the mapping G is a continuous mapping. The only potential issue would be where the denominator vanishes, but that's not an issue here. So we have a continuous mapping from S2 to S1. And now behold, if you do G of negative x, that would be equal to f of negative x minus f of negative x divided by this. Which would simplify to be f of negative x minus f of x divided by f of x minus f of x. But if you look at this, this is exactly G, but these are reversed. So this is negative G of x. Thus, we have constructed a map G from S2 to S1 so that G of x, so that G of negative x is equal to minus G of x for all x on S2. Why is this a problem? This contradicts lemma 2. Lemma 2 says there is no map from the 2-sphere to the 1-sphere that has this property. And that is where the contradiction occurs. And as you can see, that right there is the proof of the Borsuk-Ulam theorem. What remains to be shown is the proof of lemma 2. So let's go ahead and prove lemma 2. Now, if you're not excited about lemma 2, if you find it boring, you can, of course, scroll forward ahead if that's what you wish to do. But I think it's nice to go over the proof because the definition depends on winding number, and you'll get to see how we're using the property of the winding number to justify this. I think it's a nice proof, even though it's not the most exciting lemma, but it's a good way to reinforce these ideas that we've talked about before, see how they're being carefully used in the proof. So let's write down the lemma again, and then we'll prove it. So this was the lemma that we had. So you're going to assume you have a map from S1 to S1, and f of negative z is equal to f of negative f of z for all z on S1. Then the degree f is odd. So that's the lemma. So let's talk about the proof. By definition of degree, the degree of f, that would be the winding number of the following path. So you're going to take e to the 2 pi it. You're going to look at the image path, and that's what the degree is. So that's what you need to find. Now let's quickly recall how the winding number is computed. We need to recall how the winding number is computed. So let's do this. So let's set, so G is going to be a loop. So it's a mapping from 0, 1 into S1. Be the loop that's given by the function that G of t is f of e to the 2 pi it. So to compute the winding number of G, right, this is what we have to find the winding number for, and we have to show why it's an odd number. So you basically, to go back to the definition, basically what you're going to do is you're going to take this interval and you're going to cut it up into small pieces. You're going to partition that interval into small pieces so that the angle, so that the change in the angle will be small. Okay, so we partition. So actually, we're going to take advantage of this symmetry. So maybe before we compute the winding number, let's reformulate this symmetry, this type of symmetry, or maybe I should say anti-symmetry. It's not exactly symmetry, anti-symmetry. Let's reformulate this anti-symmetry using G. So if, let's say, Z is a point on the circle, and Z is written in the form e to the 2 pi it for some t between 0 and 1, then negative Z, how do we find negative Z? So the way we get the negative of a complex number, it's a rotation by 180 degrees. So we have to multiply by e to the pi I. E to the pi I, that's negative 1. So it's a rotation, but you can also say pi. You're multiplying by the angle pi. So that's the rotation angle. You're multiplying by z. So this is e to the pi I. And z, we said, is e to the 2 pi it. And now if you add your exponents together, that would be pi I plus 2 pi it. And maybe we can factor out a 2 pi I. And we're left with t plus 1/2, like this. So that's what we're getting, t plus 1/2. So here's what we've shown. So if t is some number between 0 and 1/2, then t plus 1/2 would now be a number between 1 and 1/2. So here we have an interval that's going from 0 to 1/2, and here we have an interval that's going from 1/2 to 1. And notice that negative z is, so this is what t is being set equal to. So we have, in this case, that g of t plus 1/2 is then equal to negative g of t. Right? So what is this? Well, maybe to write it out a little bit more carefully, g of t plus 1/2 would then be f e 2 pi I t plus 1/2. So then that would be f of negative z, as we've said, because this is f of negative z. And f of negative z, this is the anti-symmetry of f. This is negative f of z. And z was given by that. So that was negative f e to the 2 pi I t. So that's negative g of t. So this is the property that we have. So to summarize, so basically we have this. To summarize, if you pick some value t in the interval from 0 to 1/2, then t plus 1/2 will of course be in the other interval from 1/2 to 1, and g of t plus 1/2 would give us negative g of t. So this is the anti-symmetry property. And we're going to use this result, this relationship, to calculate the winding number and show why it has to be odd. Okay, now how do we find the winding number? So to find the winding number of G, we partition the interval from 0 to 1 into certain moments in time, into, let's say, t0, t1, into that subinterval, t1, t2, tn minus 1, tn, so that the angle changes by a small amount. Now the technical condition, so I'm just going to write here the technical condition, because I do not want to, I'm going to take it down again because that's sort of missing the point. But the technical condition is small means that if you take 2 moments in time in the kth subinterval, then g of t minus g of t prime. So I think what we said was we want the distance between these two to be bounded by 1/2, right? And then this ensures that if this is g of t and this is g of t prime, then the angle between them, when it moves, it will move smaller than pi over 2. So that means you're going to be adding all the small changes in the angles. So this is what we mean by small. You partition it so that this condition is satisfied, and then you're going to start adding up the changes in the angles that you get. But I do not want to write this because this kind of misses the point. But we're actually going to do this a little bit differently. Instead of partitioning the interval from 0 to 1, we want to take advantage of the anti-symmetry. So basically, we noticed that when we go from 0 to 1/2, and then we go from 1/2 to 1, we have this kind of anti-symmetry relationship that comes out. So to find the winding number of G, we're going to first partition. We're going to do this in 2 steps. We're going to first partition 0, 1 into 2 half intervals. So from 0 to 1/2, union 1/2 to 1. And then we're going to partition 0, 1/2 into a union of subintervals. Let's call these subintervals tk minus 1, tk, where k goes from, let's say, 1 to n. N is just how many subintervals we have. And we're going to calculate, and we're going to write, so this is where the angle is going to come into a calculation. We're going to compute g of tk. We're going to take 2 adjacent positions in the loop, and we're going to write them as e to the I theta k for a unique angle theta k smaller than pi over 2. So that's what we do. So this is basically the definition of the winding number. You make these small enough, and then you take the 2 adjacent values of the loop, you divide them, because by dividing them, you're getting the change in the angle that occurs. It's either going to be a positive or negative angle, which indicates whether or not your loop went counterclockwise or whether it backtracked clockwise. And then you have to add up all of those angles. Okay, but notice we've only done this from 0 to 1/2. And now we're going to partition the other interval. This is from 1/2 to 1 in the following form. We're going to just add 1/2 to every one of these numbers. It's going to be the same moments of time, but they're just reshifted by 1/2. This has to do with what we said in the previous line, that G has this kind of a property. So G of t plus 1/2 is negative of t, and if we have this, if we have a number between 0 and 1/2, then if you shift it over by 1/2, it's in this interval, and this is the anti-symmetry that you're going to be taking advantage of. So you first partition the interval from 0 to 1/2, and you calculate the changes in the angles that occurs, and then you take the very same partition and you're going to reshift it over by moving all of these over by 1/2. And then, okay, so we have, so thus, and now we're going to do the exact same thing. We're going to determine the changes in the angles that occur to these other partition points. So when we calculate the winding number, we have to do it for the full interval. So we calculated the change in the angle over this interval, and now we're going to calculate the total change in the angle over that interval, and we're going to have to add the 2 results together. So for this one, we're going to have f. So here's what we're going to have. We're going to do the same thing. This will be g of 1/2 plus tk divided by g of 1/2 plus tk minus 1. And this is equal to, by the anti-symmetry, this is negative tk divided by negative g tk minus 1. And look at that, the minus signs cancel away, and you're left with exactly what you have over here. So this is the same angles. These are the same angles as before. This is exactly how we're using the anti-symmetry to make this argument work. Okay, so here's what we do next. Oh, well, before we do anything, now let's say what the winding number is. So from here, we get that the winding number of G, so how do we get the winding number? It's 1 over 2 pi, and then we add up all of the angles. So we add up all of these angles, but then we have to add these angles again. We have to add these angles twice. The reason for this is because we're calculating the change in the angle from 0 to 1/2, And then we have to calculate it again over that interval. But because of the symmetry, it's the same angles again. So we have the angles just repeat all over again. So theta 2. Okay, so now it has to be an integer, right? The winding number is an integer. So in the end, we're going to get some integer. And the question is, why is this integer odd? So here's what it has to do with. So observe that g of 0 is the same thing as g of, sorry about that, it's negative g of a half would be negative g of 0. This is the anti-symmetry. Let me scroll back up again so we get to see that. It's exactly this. If you take a number from 0 to 1/2, so here's what you do. Set t is equal to 0. And then g of a half is negative g of 0. So that's just anti-symmetry. Okay, so if we add up the angles, well, let me do it like this. So if you look at g of tn over g of tn minus 1 multiplied by g of tn minus 1, g tn minus 2, and so on. This is g of t2, g of t1 times g of t1 over g of t2. This is, of course, a telescoping product. These cancel, these cancel, these cancel, and so on. So in the end, you're supposed to get g of tn over g of t0. Now g of tn, that's the last point in the partitioning, which is 1/2. So keep in mind, t0 to tn was a partition of the half interval. So that's the last one, that's g of a half. And g of t0, that's g of 0. And we said that's equal to -1. But these ratios are expressed in terms of angle changes. So this first one was e to the I theta n. And this was e to the I theta n minus 1. And this one was e to the I theta 1. I'm sorry, theta 2, e to the I theta 1, and so on. So by adding up the exponentials, we have that e to the I, and then the sum of all of these angle changes is equal to -1. Okay, and we of course know that e to the pi I is equal to -1, right? This is like a T-shirt that I'm sure you've seen. So that means that the sum of the angles, well, they do not necessarily add up to pi, but they will add up to pi plus some multiple of 2 pi because it's periodic. So it's going to be 2 pi times some integer, let's call it capital N, for some integer n in Z. So now we can complete the proof, because what was the winding number? Let's scroll all the way back up. Look at the winding number. The winding number was 1 divided by 2 pi. It's the sum of the angles from 1 to k. I made a small mistake here. I guess I should have said this was n. A small mistake. This should have been n. Should have been n. So the sum of all of these angles, and then it just gets repeated twice. But the sum of the angles from 1 to n adds up to this. So thus, the winding number of G is 1 over 2 pi, and you add up the angles, and then you add up the angles again. And now we get to say what these are. This is pi plus 2 pi n, and this is pi plus 2 pi n. So this is 1 over 2 pi, and pi plus pi, we get 2 pi, plus 2 pi and 2 pi, so we get 4 pi n. And when we divide everything by 2 pi, we get 1 plus 2n. And whatever this is the definition of an odd integer. So that completes the proof of this lemma. So as you can see, this is a pretty technical lemma, but I think it's a nice argument. We get to use the winding number again carefully. It's not too bad, and it's nice and rigorous and all that. So now let's mention a very surprising result, and then we'll finish up with the Borsuk-Ulam theorem. We can use this theorem to prove a very surprising result in topology. You can even say this is a result in geometry. And it has a very funny name. It's called the ham-sandwich theorem. So before we say what the theorem is, let's motivate what the theorem is saying with an example. So it's called the ham-sandwich theorem because you have a sandwich. So you have like a piece of bread. So this is like a piece of bread. It does not have to be symmetrical. Most pieces of bread are not. It's not like a nice circular shape. And then you have another piece of bread above it. And it could be larger because in real life, they're never going to be the same size. In fact, it might even be a little bit displaced or something. So then you have another piece of bread that kind of goes like this. And then in between the two pieces of bread, you put some kind of food. So whatever you want, whatever your favorite food is. So you have something, and it could be larger than the bread itself. So maybe it's a lot bigger than the bread. So something in between the two pieces of bread, and you can see it overpours, overflows. And the ham-sandwich theorem says that you can take a knife and you can cut it in half in such a way so that you can cut with a knife so that each item, so each food item, so this would mean the first piece of bread, the second piece of bread, and then the whatever you have in between, so that each item gets cut, gets bisected exactly in half. Let's put an exclamation point because it is fairly surprising. So what the ham sandwich theorem basically is saying is if you have a ham sandwich, you can share it with someone else perfectly. Everything can get cut in half. Now what makes this surprising is if you have a single piece of bread, so I'm going to draw this as a two-dimensional picture. If you have a single piece of bread, so let's say this is bread, the fact that you can cut bread in half, that's not really surprising. There's lots of ways to do it. So all you do is you're going to draw some kind of line, and clearly this line, there's more bread on this side than that side, and then you're just going to move this line a little bit over to the right. So you move it a little bit over to the right, and now you have more here than there, and now you move it a little bit over to the right. You have more here than there, and you keep on moving it over to the right. So as you keep on moving it over to the right, at some point, and this is sort of like an intermediate value theorem if you think about it, it's increasing, 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 and at some point, right, at some point it's going up. At some point it has to reach exactly half its area. And then you would get to the point where half of the bread on the left and half of the bread on the right is exactly the same. So, but what makes this theorem surprising is because you're not cutting one piece of bread, you're cutting three different things at the same time. You have to understand that if this blue line cuts this bread in half, it does not necessarily cut the other bread in half because these two pieces of bread might be completely different shapes. They do not have to be perfectly aligned or anything like that. And if you try to then adjust the line to cut the other one in half, maybe you mess it up and the first piece of bread is not being cut in half. So it's by no means obvious that you can do this. So this is called the ham sandwich theorem. Let's say what it says a little bit more precisely. So here's the precise statement. So it says that let A, B, and C be three bounded solid bodies in R3. We understand what bounded means. If you are wondering what it means to be a solid body in R3, it's just a subset of R3. That's all it is, just a subset of R3. And if you want to be a little bit more technical, you would add, which are what is known as measurable sets. Measurable basically means it's something that has a defined volume. That's what I mean by a measure. So notice we are in three-dimensional space. So when we talk about size, we talk about volume. If you're on the real line, one-dimensional measure would be length. Two-dimensional measure would be area. Three-dimensional measure would be volume. So this is an idea from real analysis. When you have a region in Euclidean space, you talk about the measure of the region. You talk about how much space it takes up. That's what we call the measure. Now, you have these pathological examples of regions for which you cannot assign a notion of measure. So not every subset has a measure to it. So it's something that's a bit bizarre, but that's just, when you do math for long enough, you realize that if you allow yourself to talk about every conceivable subset that you can possibly have, then that's not really surprising. You have all sorts of strange things that happen. But practically speaking, you never come across regions which are not measurable. So that's the technical condition. If you've taken maybe an advanced calculus course, you probably recall they talk about these things called being Jordan measurable, but let's not go there. If it bothers you, you can think of A, B, C as being polyhedron, because polyhedron can always be assigned a measure. So we have three solid bodies in R3, and what we're saying is we can find there is a plane. Let's call this plane pi, capital Pi. There's a plane in R3. So the plane represents a knife, right? That's the cutting plane, that's the knife. There's a plane in R3 which bisects A, B, and C simultaneously. So you have some kind of solid body or something. This is A. This is a solid body. You're saying that there's a plane. There's a plane. Pi. That it would cut it into two portions. So if you want to think about what that means is you can take A, intersect pi, and then take the complement, and then you get two remaining pieces when you remove the intersection. And that's what you're saying, is that these two pieces will have the exact same measure. So measuring means volume. This volume would be this. But there's a plane that does it simultaneously to all three solid bodies. So that's a pretty surprising result. And interestingly, we're going to prove this using the Borsuk-Ulam theorem. Now, in order to prove this, we're going to make an assumption. So this is going to be our proof. Without loss of generality, we can assume, by the way, these three bodies, they do not have to be disjoint. Though if they're not disjoint, then this is a little bit silly. Like, what do we mean by a ham sandwich? That does not exactly make sense if they intersect. If the two pieces of bread intersect, that's not going to make sense. But I mean, practically speaking, I guess you want them to be disjoint, but when you prove this, they could overlap. That would be fine. So without loss of generality, we can assume that A, B, and C are all contained inside S2 because they're bounded, right? We're saying that you have the two-dimensional sphere, and then the three bodies. This is sort of like body A. This is maybe you have another body, body B. Then you have another one. They're all sitting inside the two-dimensional sphere. So this is the unit sphere. Because if it's not the unit sphere, then you will just blow up your sphere and you will repeat the argument all over again. Topologically, the size of the sphere does not matter. So let's just assume it's the unit sphere. Okay, so they're all sitting inside the unit sphere. So here's what we'll do next. For each, so as we're writing this proof, you should sense that this feels a little bit more geometrical because sizes are now beginning to matter, something that we've never really paid attention to before. But anyway, for each point, let's say Q on S2, let L of Q denote the line which passes between Q and 0. And when we write 0, we just mean the origin in R3. So if you find that confusing, let's redraw the picture again. This is our two-dimensional sphere. And then somewhere inside, we have 0. And then we have a point, Q, on the sphere itself. And between 0 and Q, we can draw a line. And this line is what we're calling the line at Q. So we should note that the line at Q and the line at negative Q are the same line. Because whenever you draw this line, it intersects it at the antipodal point. So the line at Q and the line at negative Q will give you the same line. And now we're going to define a point on this line. So we're going to pick I'm thinking about what notation to use. So let's write it like this. So let P of, let's say, L of Q, comma A, this is going to be the unique point that's on this line, L of Q, so that the plane pi at P and perpendicular to the line bisects the body A. So this might be a bit confusing when you write it out using words, but the picture will make it a lot easier to understand. Let me draw a larger picture for you. This is our sphere. And within the sphere, we have a body completely contained inside the sphere. This is what we're calling body A. You can do this for any one of the three bodies. I'm just doing it for body A, but the same type of definition can be made for the other three bodies. And you pick a point, you pick Q anywhere, right? So let's say you pick Q right over here. Let's say this is Q. You're going to draw the line. So this is the origin. And the line, it's the line that passes between the origin and Q. This is L of Q. And as you know, anytime you have a line you can talk about the plane that's perpendicular to that line, right? The perpendicular plane. So what you start doing is you first begin drawing a plane that is, let's say, outside of the sphere. So here's a plane that's perpendicular. That's a plane that's perpendicular outside. It's perpendicular to the line, but it's outside the sphere. Now, notice it's not bisecting the region. But you can take that plane and you can move it a bit closer. So you move it a little bit closer inside. So then here's your plane. Now you can see that your plane is cutting a piece of it, but it's not cutting it perfectly in half. So it's exactly what we were saying earlier. By the intermediate value theorem, this has some finite number. Let's say this has a volume 15 units. So when you draw a plane, the moment it touches it, it's going to be some small number. And as you keep on moving it in one direction, the volume will grow. It will get bigger and bigger and bigger. By the intermediate value theorem, you're going to reach 7.5. You're going to reach the midpoint, the bisection of the volume. It does not matter how this is positioned. You can position the line anywhere. With respect to that line, you can always vary the perpendicular plane until it perfectly bisects, right? So at some point, it will perfectly bisect this in half. So we'll cut it perfectly in half, and you achieve a bisection. And the point through which that plane passes, we call it P. Now, this would be a little bit ambiguous, so we indicate that the point, it depends on the line, and it depends on the body. If you have a different body, you will have the point positioned so if the body is here and you have another body here, then maybe you position the point somewhere else. But whatever the point is, it's living on that line. So that's how this is being defined. And now we're going to, and of course, as I indicated, we're doing it with respect to A, but you do the same thing with respect to each of the three bodies. And now you're going to define, now construct the function. Let's call it f subscript A. So this is going to be a function from 2 to r, and it's going to be defined by the rule that f a of a point q is going to be the distance between q and p. So this f is the distance function. That's the unique point, that's q, and that's just the distance between them. So this, if you fill it in here, that's the distance between them. So it's the distance between q and p. So this is, of course, the Euclidean two-dimensional distance. But of course, using our notation, the way we calculate the point, it's the point that depends on the line, of course, and it depends on A. So that's how it's being defined. So you do this for each of the three bodies. So maybe what you're beginning to notice is this is a pretty clever proof. This is not something that one would typically do themselves. There's quite a number of things you have to define first before this can even be, before you can work this out. But anyway, so that's how you construct these three functions. And you do this for every body. We're just defining it for body A, but you do it for the other two bodies. And here's how we're going to use the Borsuk-Ulam theorem. Now, before we use the Borsuk-Ulam theorem, we are, of course, taking advantage of the fact that this function is continuous. One can, of course, be skeptical and ask why it is continuous, but I think that's pretty believable. We're not writing out every conceivable detail, but just enough so we get to see something that's fairly believable. So anyway, we have this function, and now we're going to take advantage of the Borsuk-Ulam theorem, so we need to map S2 into R2. So here's how we do it. So finally, construct the function. How many functions did we already construct? Let's count. So we did construct the line, and this is a point on the line. I guess you can call it a function that depends on the body and the line. Then we constructed these. There's technically three of them, and now we're constructing another one. So finally, we're going to construct a function. Let's just call this one f. And this one's going to go from S2 to R2. So this is where the Borsuk-Ulam theorem is going to come into play. And it's going to be defined as follows. By the rule that f of q is going to be equal to f of aq minus f of cq, and then f of bq minus f of cq. So I'm not in any way saying that this is like a motivated proof. Like when you first see something like this, of course, the immediate question is the people who came up with the proof, what exactly were they thinking that led them to this kind of idea? But we're just trying to understand how it works. We just want to see how it gets proven. So we define this kind of function. And by the Borsuk-Ulam theorem, there is a point, it's called Q0 on S2, so that f of Q0 is equal to minus f of Q0. Sorry about that. I meant to say these have to be antipodal points. F of minus Q0. But f of minus Q0 would be equal to fa of minus Q0. So I'm just using how this function is being defined by putting it into these pieces. So it's f of a minus Q0 minus f of c minus Q0, fb minus Q0 minus f of c minus Q0. Now, here's the part which is kind of interesting. Let's understand what this is in our picture. The picture will make it easy to understand. So if you have a point Q, fa of Q is the distance from Q to P, where P is the bisection point on the line. Now, if you replace Q by negative Q, you go to the antipodal point. When you go to the antipodal point, the line will remain the same. L of negative Q is still the same line, but the distance from this one to that one, from this point to that point, would be the diameter, right? So it's the diameter has length 2. This has a certain length, so it's the remaining length, which is 2 minus that length. Okay, so right, it's just the same. The points on the bisection point will remain the same. It's just the other side of the distance. So since the entire diameter has length 2, this is a unit sphere. It's just 2 minus whatever that is. So you can therefore replace this. This would just be 2 minus fa of Q0 without the negative. This would be 2 minus fc Q0 without the negative. This would be 2 minus fc Q0. And this would be 2 minus fc Q0. So this simplifies. F of negative Q would then be, so we have 2 minus 2, we have minus f of a, and then double minus. We have minus fa Q0 plus fc Q0 minus fc Q0 plus fc. I'm sorry, I meant to say this should have been a b, of course. That should have been a b. That should have been a b. Q0. And if you look at what this is actually exactly how you started, right? It's exactly this map, the one you have over here, but it's the negative of it. So it's the negative of f of Q0. So now look at this. F of Q0 is equal to f of minus Q. And f of minus Q is minus f of Q0. If you put these together, we have f of Q0 is equal to minus f of Q0. So in other words, that means that f of q0 is 0, right? The only vector which is equal to itself is the 0 vector. Of course, when we write 0, we mean the 0 vector in R2. So what does that mean? That means that the function at this point q0, it vanishes. So in other words, thus f a q0 minus fc q0 is 0. And so we're just talking about the two components. This is our function at q0. This component, both of the components have to vanish. This component vanishes, and this component vanishes. And fb of q0 minus fc of q0 is also 0. So putting this together, we conclude that fa of q0 is equal to fc of q0, but fc of q0 is equal to fb of q0. And at this point, the proof is almost finished. You just have to recall what these functions represent. Let me scroll back up again so we remind how these functions are defined. So you have a body, A, sitting inside your two-dimensional sphere. And you have a point, so in this case we have Q, but we have a one point Q0 for all three regions. And FA of Q0, so FA of Q0, that would mean it's the distance. So it's a point on this line. So on this line, you're going to find the point that bisects the region, right? It bisects the body. And FA of Q is just the distance between the bisection point and Q, right? So, and we're saying that you have one point that works for all three of them. So this represents the bisection point. So let's maybe say it in words. So we can find a point Q0 on the sphere so that the bisection points on the line L of Q0 all have the same distance from Q0. In particular, all three bisection points coincide. And so the plane from that point cuts all three regions. So hopefully this is clear, but let me try drawing a picture to try to clarify this if there's some kind of confusion. We have our sphere again, and notice we found the point Q0 that simultaneously satisfies these three conditions. So Q0 is somewhere on our sphere, and through that point we have a line, and on that line FAQ0, this represents the bisection point. So somewhere on this line there is a bisection point. Let's say it's located over here. That's P. That's the bisection point. And FA of Q0, that's the distance between Q0 and P. And this is the bisection point that bisects this body. So this just means that if you were to draw a plane through that point, it will bisect this region A. But now we look at, let's look at FB of Q0. FB of Q0, it's the same number. FB of Q0, it represents a point somewhere along the same line, Q0, that bisects B. But it's the same exact distance away from Q0. So it cannot be in a different location, because then it would mean this distance and this distance are not the same. So they all have to be in the same location. So there's this one point. It's all the same distance. And this plane, pi, that we found, is then by construction the plane that bisects A, B, and C. So therefore, we have found a plane that bisects all three solid bodies simultaneously in the plane. And that right there is what we call the ham sandwich theorem, and that's the way you prove it.